right, ladies and gentlemen, today's class recording has started, so make sure we're not doing anything dumb. Okay. All right. For the past week, especially the last couple days of last week, we've been talking mostly about the nucleus of the atom. Talking about how many protons an atom has, how many neutrons the atom has, and we can identify those a little bit more clearly because protons and neutrons are all in the same place. Where do we find protons and neutrons within our atom? In the nucleus, right? They're always in the nucleus, they're always in the same place, so it's a little easier for us to identify those factors or those parts of the atom. But those aren't the whole part of the atom, right? We know that electrons exist. So if we're going to come up with a model that represents the entire atom, that model or that theory has to include our discussion of electrons. How do we know that electrons exist? When did we first discover electrons, or when did we first have evidence that they existed? Or who is responsible for sort of discovering an atom? Go ahead. Thomson, right? Thomson does what experiment? Go ahead, Claire. The cathode ray tube experiment. And from the results, from the observations made during the cathode ray tube experiment, we have evidence that there are these small, negatively charged particles that exist, subatomic particles smaller than the atom. So, we try to figure out, okay, well, where are those electrons? How does this whole picture of the atom come together? And it starts with something that we call the Bohr model of an atom. Okay? So far, sorry, should have done this beforehand. Okay. All right, people. I said there were 4 people that I wanted you to know, right? All right. Who do we first sort of credit with the idea of coming up that atoms exist? Back in ancient Greece, who's the person that sort of came up with that atom that Democritus. So Democritus is the first person that we sort of credit that atoms exist, okay? So then we come up to Dalton. Dalton's atomic theory. Why is Dalton's atomic theory important? Dalton's atomic theory says that atoms are the smallest, but it's important why? Evidence to back it up, right? So Dalton's atomic theory is evidence to back it up. So then we talked about Rutherford and cathode ray tube experiment and electrons, and then the last person we talked about is, Thomson and the cathode ray tube experiment, okay? Then last person we talked about was Rutherford. What experiment did Rutherford do? Gold foil experiment, and what's the gist of the gold foil experiment? What's the most important conclusion you get out of the gold foil experiment? Somebody said it. The nucleus, right? That there's this small positively charged center of the atom that we call the nucleus. Okay, so Niels Bohr. Okay, Niels Bohr is a Danish scientist, and we're looking here time-wise now like early 1910s. Okay, like 1912, 1913-ish. Okay. So Niels Bohr comes up with a model or a theory that we call the Bohr model of the atom. And in his Bohr model of the atom, he says that electrons exist around the nucleus in defined shells. If I asked you to draw a picture of an atom, most of you would probably draw a Bohr model. Okay? You would draw a little nucleus in the middle, positively charged, right? And then you'd have like little rings that go around it, yes? Right? You kind of see that on like radioactive signs and things like that. Those sort of pictures of an atom are representative of a Bohr model, where those rings that go around the nucleus represent the paths that these electrons take as they're traveling around the nucleus. And so, right, looks kind of like a solar system, yeah? Right? Sun's in the middle, nucleus kind of represents the sun, and then the electrons sort of represent the planets like orbiting around the sun, right? So sometimes we'll call this a planetary model, okay? But there's more to it than just the fact that these electrons travel in these orbits or these shells around the nucleus. Okay? What Bohr says, and he's got evidence to back this up, is that these shells correspond to different energy levels. And I seem to recall this from last year, that some of the things that in the outline are a little out of order. Okay. That shells closer to the nucleus contain lower energy electrons than the ones that are farther away. Okay? I think that's down number 7 down there to the bottom. I don't remember why I put it there, but okay. So if you go Roman numeral 1, letter B, number 7. All right, good with this basic stuff? Okay. So let's use an analogy that hopefully will make it make a little bit more sense. So let's talk about this ladder. Okay. All right. As you go up the ladder, what happens to your energy? It's increasing. Specifically, what kind of energy? Gravitational potential, right? That as you go up the ladder, your gravitational potential energy is increasing. Good? Yes? Okay. But here's the one thing that makes the Bohr model important. Just like this ladder, while yes, generally speaking, as you go up the ladder, your gravitational potential energy increases. There are only certain amounts of gravitational potential energy that you can have, right? When you're on the ladder, you can be on the lowest step, or you can be on the next step, or you can be on the next step, or you can be on the next step. But you can't be in between steps. You're either on this one or you're on the next one, but you're nowhere in between. Good? Okay? Is it possible to move from one step to the next step? Sure. What do you have to do? You have to walk up it. What would that mean energy-wise? You would have to increase the amount of energy that you have. Is it possible to go from a higher step to a lower step? Sure. What has to happen? Decrease in energy. Okay? While we're not talking about gravitational potential energy here, we're talking about electrical potential energy because we're dealing with a negative charge and a positive charge. What do negative and positive charges try to do to each other? Attract, right? When they are close together, there's not a lot of potential energy, okay? But as we move them farther and farther apart, right, what are they trying to do to each other more and more? Come back together, right? If we move them pretty far apart, that's a lot of potential energy. So here, on this ladder, as we go up the rungs of the ladder, the amount of energy increases. Just like on Bohr's model, if you move from a lower shell to a higher shell, your potential energy increases. Okay? Good with that idea? All right. So, the shells in Bohr's model are representative of like these rungs on the ladder. The electrons have to exist in a shell. There is no in between those different shells. Okay? And we call this idea quantization. The idea that based on where the electron is, that determines how much energy it has. Okay? So this idea of quantization. Okay? So these shells are quantized. That's what it means, right? They contain definitive amounts of energy. And more important for our discussion going forward, which shells have the greatest amount of energy? The ones farthest from the nucleus, the ones farthest from the nucleus. Just like when you climb the ladder, you have the most potential energy up at the top of the ladder, right? You have the most ability to do damage up at the top of the ladder than you do towards the bottom of the ladder. Okay. All right, good. it is possible for these electrons to move between different rungs of the ladder, or different energy levels. They have to gain energy by going, in order to go up to a higher level, but then they have to lose that energy in order to come back down. So once you're on a level, that doesn't, you're not necessarily stuck there, but there has to be a way for you to move from one to the other. And that's by either gaining or losing energy. Okay? If we pull out a term that we introduced way back when we were talking about energy, what do we call it when the amount of energy that something has changes? Negative. Well, the negative could be part of this, but what do we call it when the energy of something changes? What do we do to that object? The W word. Work, right? Work is a change in the energy. What kind of work do we do to make the electron go up to a higher level? And what's happening to their energy? It's increasing. So what kind of work is that? Positive work, right? When they fall back down to lower energy levels, what are we doing? Negative work, or we're decreasing their energy, okay? So these terms that we apply, even though we're not talking about lifting an object up to a higher level, we're talking about electrons as they move around the nucleus, it still applies. Work causes the energy of the electron to change. We do positive work to increase these levels. We do negative work to decrease the level. Okay? Good with that idea? All right. How does this apply? Well, take a look above you. Okay? Wow. See these lights? Yeah. Okay. These lights, what? These lights are filled with atoms. And each of those atoms has a nucleus, and it has electrons that go around that nucleus. Okay? So, when we turn the light on, what are we doing to the electrons that are in the atoms that are inside these light bulbs? We're doing positive work on those electrons. Where is that energy coming from? What does the positive work? The electricity, right? The electricity from the wall increases the energy of those electrons. But, just like anything else, if we increase the potential energy of something, it generally speaking doesn't want to stay there. As a rule, things try to get to the lowest energy level that they can achieve. If I take this tennis ball and I raise it up in the air, what have I done to its potential energy? I've increased it. But if I let it go, where does the tennis ball go? Down. So, pay attention to these questions because they're the first of like about 1,000 times that I'm going to ask you these questions. It's right next to your left. So, why does the tennis ball fall to the ground? No. Gravity is not the reason why it happens. Gravity is how it happens. Let's talk about it from an energy standpoint. When I raise it up in the air, what happens to its potential energy? It increases. What we find in the universe, out there in nature, things that have high potential energy will look to get rid of that potential energy. I raise the tennis ball in the air. Is it high potential energy? Does it want to stay there? No. Any chance it gets, it will look to get rid of that potential energy. How does it get rid of gravitational potential energy? Falls down. What happens to that gravitational potential energy? Turns into kinetic energy, right? But we end up with less potential energy than we started with. Gravity is how it happens. Why it happens is because it gets to a lower potential energy state. Okay? Here, these two terms over on the right-hand side. Okay? ground state, excited state. In terms of energy, what's true about the ground state? Has a low potential energy. Where's the tennis ball right now? On the ground. How much potential energy does it have? Low amount, right? Ground state. If we move it to a position that it has a high amount of energy, what is this now? This is excited state, okay? It has a high amount of potential energy. Does it like being in an excited state? No, right? It will try to get rid of that potential energy and turn it into something else, okay? So, Jeff, going back to what we just talked about, the electrons that are in these atoms, that are in these light bulbs, right? The electricity makes them move where? Say again? Where does the electricity make them go in terms of their, to talk about within the atom itself, right? Naturally speaking, where do the electrons start? Which we call the what? The ground state, okay? The electricity makes them move to a what? To an excited state. The electricity does work to increase their potential energy. But, Maggie, I'm going to go with you on this, right? Do they like being in that excited state? No, they look to go to a ground state. But what do they have to do before they move back to the ground state? Get rid of that energy that the electricity gave it to them. How did these electrons get rid of their energy? They produce light. All right? This light that is coming out of these light bulbs is because the electrons move up to an excited state, because the electricity makes them move up to an excited state, but they don't like being there, and so then they fall back down to their ground state, but giving off energy in the form of light as they do it. Okay? Which I'll switch closer to the front of the room, but okay? Why does this happen? There's no electricity going in the light bulb. What does that mean? They don't move to the excited state. If they don't move to the excited state, do they have to give off any energy? No. Nope. And they just stay in that ground state, and that's called the light is off. Right? We call it the light is off. Alright. Just like the ladder, the different steps on the ladder correspond to different amounts of energy. And that means we know exactly how much energy we need to gain or we need to lose. What happens on the ladder if you don't gain enough energy? What happens on the ladder if you try to step to the next step, but you're not paying attention and you don't step high enough? You fall where? Well, or whatever step you started on, right? You go to take a step, you don't hit the step, you end up right back where you started. Same thing with these electrons, right? If we don't give them enough energy, they won't make it to that excited state, and they'll remain in that ground state. So very, very these states are very, very rigid. You're either here or here or here or here, but nowhere in between. Okay? Good? Okay. Yeah. It was good. Everybody else good? Yeah. All right. We run into a problem with Bohr's model of the atom. Bohr's model of the atom accurately describes hydrogen. It works great for hydrogen. But what's the deal with hydrogen? It has one electron. So when you're only talking about one electron moving around in these different steps of the ladder, Bohr's model, awesome. All of his calculations turn out exactly right. Everything works great. But only one electron. If you get any more than one electron, so as soon as you go to helium, Bohr's model works pretty well, but it's not completely accurate. All right? So, what we find out is this idea of an orbit or a shell is not what is happening here, okay? That electrons don't actually exist in a shell, all right? That, yes, the farther away that an electron is from the nucleus, the more energy it has, right? Oh, sorry. The further away that this object has from, or the further away the object, the further away, take like 47. All right, this is live. We're doing it live right here. We can't edit this. All right. The further away an electron is from the nucleus does mean that it has more energy. And the closer it is to the nucleus does mean that it has less energy. But it's not those rigid levels like Bohr's segment limits. Okay? Good there? All right. I don't think we're going to get through the next part with the Broglie, so why don't we call it a day today, okay? Hold on one second. Before you start packing up, you'll have plenty of time. Hold on. Stop. So, first, I'm not going to be in class tomorrow. I know. I have to go. You remember that meeting that I went to like last week where I was gone the whole day to talk about science curriculum? So,
Are you still recording? I would like to.
Yes. So anyway, I'm going to be out again tomorrow. So what I probably will do, hey, listen. What I probably will do is I will link a video here to tomorrow's date on the calendar. And I'll have you guys watch a video that introduces and kind of goes through the next part of this outline. Okay? I know that's not the most exciting way to spend class, but at least it gives you guys the information and we don't waste an entire day. Hold on a second. Hold on. Stop. Freeze. So, totally destroyed my table, and then you didn't freeze when I asked you to freeze.
It's not completely destroyed.
All right. If you have not done so, first there was a couple of pages from the book that I kind of had listed on Friday's calendar that introduces you to the idea of Bohr's model of the atom. So that will give you a little bit of reinforcement of what we did in class today. Then there's also a couple other pages that will get you into what we're going to talk about tomorrow, dealing with Heisenberg and his uncertainty principle, and Schrodinger, which is his quantum mechanical model of the atom. Okay? Schrodinger, there is, yes, and there's a part of that that is, the Schrodinger's cat will be important to our discussion. Not like super important to our discussion, but will apply to our discussion a little bit later, like Wednesday, Thursday of this week. Okay? So, if you're looking for some reinforcement of things that we did in class, you can find some pages in the book right there that will lead you to the, what we're talking about today and tomorrow. Okay? All right. So I will see you guys on Wednesday. Enjoy your video tomorrow. It will be super boring, just listening to me talk, but I won't actually be in front of the class. I'll just be like playing with it. Yeah.
I love that.